Okay.
Hello, everyone. Welcome to the MIF++ seminar. It's a great pleasure to introduce Professor Steve Scheiner. I hope I pronounce your name correctly, from the State University of Utah, right? Who will talk about hydrogen bonds in the context of proteins. So the exact title is Origins of and Contributing Factors to H bonding, Implications for Protein Structure. Over to you, Steve, please.
Okay. Well, I'm glad to see people are here for this. So let me get started and I'll explain hydrogen bonding from the ground up. So let me start with the very basic concept that that's a molecule. Molecules are sticky, by which I mean there's a lot of different forces by which they hold together one to another. So the longest range force is electrostatics. So that's what you remember from physics. We have pluses and minuses, and they attract one another. So molecules, even if they're neutral, they're going to have a charge distribution on them, plus, minus. And by that, I don't mean full-fledged charge. I just mean partial charges there. So if another molecule comes up to it with its own sets of charges, there are going to be some attractive and repulsive forces between them. And electrostatics will be the longest range force. And so notice I haven't said anything about hydrogen bonding yet. Hydrogen bonding is sort of a special case of this. So another major force in the interaction between the molecules is London dispersion. And that arises because there's instantaneous, very momentary charge buildups that occur, maybe a plus here and a minus here, which lasts a microsecond. And when it's there, it tends to induce charges on the other molecule. And then we get a little bit of an attractive force. So dispersion is a short range force. It's something like R to the 6th in its long range. So these are the forces that are going to attract molecules together, regardless of whether there's a hydrogen bond there or not. So how does a hydrogen bond fit in? Well, first, let me again sort of generalize. Here's A, X, B. Now, in general, anytime we have a bond like that between A and X, this bond will typically be somewhat polar, and there'll be a little charge on one group like that, a little plus, a little minus, a sort of dipole. And this base, I'm using letter B, it's a base or a nucleophile, typically will have a slight negative charge. So again, there will be an attractive force between the two. So how does a hydrogen bond differ from those? Well, it doesn't really. It's just the bridging atom happens to be a hydrogen. So if this bond is polar, there'll be some plus, some minus, and minus there, and we have an attractive force. So hydrogen bonds are largely electrostatic. That's sort of the major force that goes into them. But it's not the only one. There's also a charge transfer component to that. And the way that works is, I don't know how much chemistry you guys may remember, but there's an AH bonding orbital that looks like that. There's also an anti-bonding orbital that looks like that. So this would be sigma, and that's anti-bonding. When a base comes up, it has a pair of electrons, and some of these electrons, a little portion of it, transfers across like that. That's what's meant as charge transfer. So this charge transfer element is sometimes called N to sigma star. So N is another notation for lone pair because it's non-bonding. So hydrogen bonding has an electrostatic piece, it has a charge transfer piece, and there's also dispersion. So what makes the hydrogen bond unique? In some ways, not much. It's not very unique. But unlike some of the other things, it tends to be fairly directional. So if we have an AH bond, this base can be coming from a lot of different directions. If this was purely electrostatic, it wouldn't matter a lot which direction the base came from. But partly because of the charge transfer and other issues, it much prefers to come in along that way. So hydrogen bonds have a strong tendency towards linearity, and you'll see that term a lot, which means if there's an H and a base, this angle theta tends to be around 180 degrees. That's its preference. Can I ask by a quick show of hands, how many of you guys are crystallographers?
Well, if you
Okay.
count mathematical crystallographers as well.
Okay, I'll count them all. So I'm going to present one other piece to that, which is kind of important. Some of you may be familiar with something called a cone correction. And what that means is if you tabulate the probability 180, 170, 160, 150, although, as I said, there's a tendency towards 180, if you do a histogram of these things, it'll look more like this. And that's because of what's called a cone correction. Because if you have something like this, something coming in at 180 degrees, there's a small cone that encompasses 180 degrees. If it's coming in at a larger angle, that's a bigger cone that encompasses it. So if you do a survey of hydrogen bond angles in crystals, you'll see it looks like this up here. But that doesn't mean there's not a linearity preference. Okay, so I'll just leave that for here without going into the math because I wanted to make that point. Okay, so the next thing we get into is what groups participate. So symbolically, we have that. So what will tend to form a hydrogen bond? Well, as I said, one of the strongest elements is this polarity. So in chemistry terms, that means the more electronegative the A is, the more it polarizes the AH, and so the stronger the bond it will make, more polar, more electrostatic. So in chemistry, if you guys are familiar with electronegativity, F is the most electronegative, then O, then N. So historically, these were the atoms that were considered most likely to form a hydrogen bond. But as time went on, it was realized this was not correct. As you move down in the periodic table, you also get a possibility of hydrogen bonding. So just in the halogen bonding, Cl, Br sometimes, Nitrogen, well, phosphorus, oxygen, S or Se. So the range of atoms that could serve as hydrogen bond participants enlarged. Language. This A is frequently called the proton donor for obvious reasons, and that's how most literature will refer to it. But as I said before, the electron density is going that way. So the AH group is also the electron acceptor. So you have to be careful in the literature with the language. Most commonly, they'll call it the proton donor, sometimes the electron acceptor. Likewise, B, it's called the base. It's sometimes called the nucleophile or the electron donor. And again, the stronger the basicity of B, the stronger the hydrogen bond is going to be. Okay, so factors that control the strength have to do with the groups, what A is and what B is, what atoms. But let's say we take something like a nitrogen here. So nitrogen can be a proton donor. Things that will make it a stronger proton donor. So what we want to do is build up positive charge on the H. So anything that sucks electron density away will strengthen this as a hydrogen bond donor. Things that suck it away are called electron withdrawing groups, EWG in chemistry. Electron withdrawing groups are things that are electronegative, like chlorine is an electron withdrawing group. You can also put groups, not just atoms. So any electron withdrawing group that's bonded to the actual proton donating atom will strengthen it. Likewise, on the base, what it wants to do is donate its electrons away from here to here. What will allow that to happen is any electron donating group on the base that would help push electrons that way. Electron donating groups are things like alkyl groups, things like C8 methyl, ethyl, and so on. NH2 is an electron donating group. Okay, so we could strengthen or weaken a hydrogen bonding group depending on what we put on as substituents on the two groups, both the proton donor and the proton acceptor. Another factor is where we get more into chemistry, and there's a concept called hybridization. So a methyl group or a carbon that has three things attached to it in addition to the hydrogen, it has a total of 4 substituents. We call that sp3 hybridized. A carbon that has only 2 groups to it, so we typically have a double bond and a single bond, and here's the H. So to have this double bond, that would be sp2. If the carbon is triple bonded to something, that's sp hybridization. And it turns out that the sp hybrid is a better proton donor than sp2, which is better than sp3. So if you see a carbon which is triple bonded to something, it's more likely to act as a proton donor than as a proton acceptor. Okay, now I've tricked you a little bit because here I've been talking about carbon as a proton donor. Classically, it's not, because the electronegativity of carbon is very similar to hydrogen. So when you take a CH bond, the charges there are almost zero, very small charges, which makes carbon a poor proton donor. So for years in the chemistry community, anytime someone suggested CH as a proton donor, people laughed at them or disparaged them, and they said, no, that doesn't happen. But we've learned in recent years, last 20 to 30 years, that's not true, because the factors I mentioned before allow it to be. So the hybridization, if carbon is sp hybridized, yes, it can be a proton donor. In fact, this is hydrocyanic acid. It's a pretty strong acid, and this is well known to form hydrogen bonds. So put carbon in sp hybridization, and it's quite likely to form a hydrogen bond. The other trick, even if it's sp3, so it has 3 groups, if you put one or more electron withdrawing groups here, that enhances its ability to act as a proton donor, and it can. So things that are electron withdrawing groups, as I mentioned, would be halogens, F or Cl. Another one is an amide group or peptide group. So I think you guys are interested in proteins. So here is a typical amino acid. So these are peptide groups, as would occur in a protein. These are suckers of electron density. They're electron withdrawing groups, which makes this H quite viable as a proton donor, as a hydrogen bond donor. Now, having said it can form a hydrogen bond, I haven't really said how strong it is. And in most cases, the CH is poorer than OH or NH. So that's an important effect that, so let me make sure you can see the screen and you can hear me. Yes? Okay. So did you get this where I was talking about the peptide business?
Yes.
Yes.
Okay, so this is a C alpha, which is common of every linkage in proteins. So every amino acid has a C alpha H on it. But without taking a lot of the time that my successor will be speaking about when he talks about proteins, I'll just mention that there are a number of protein residues, which is this R group, which also contain a,
Steve, I think you lost your screen.
yep. I think what happened is I need to go back to share. Go back to the Zoom. Go back. I need to I left this. Okay, it's coming back on.
Recording in progress.
Share. And let me make sure I can share now. So there are a number of different groups that are on the protein, each of which have CH groups. And so Zygmunt, I'm sure, will be talking about that at great length, so I'll go on beyond that. Okay, so the energy of hydrogen bonds. What I indicated a few minutes ago is that CH is weaker than OH or NH. How much energy comes out of that? So the field that I work on is ab initio calculations, which are, you could think of these as gas phase. So if, for example, in this classic case of the water dimer, in our frame of reference, when we calculate this interaction, this corresponds to the energy of interaction of two water molecules and nothing else. This is not in solution, it's in the gas phase. And this interaction energy is 5 kilocalories per mole. For those of you who deal with other units, this would be 20 kilojoules per mole. So this 5 is kind of the standard, the reference. If something is up to 4 or 5 kilocalories, or even 3, we would consider that a substantial hydrogen bond. It's not the limit on hydrogen bonds, they can be stronger. So as you're reading in the literature, if you're reading ab initio calculations or gas phase, these are the sorts of numbers you look at. Whereas when you put this into solution, so if I take any hydrogen bond and I surround it by stuff, by which I mean put it in solution, put it in a low temperature matrix, that is going to change the hydrogen bond energy. Typically, it will make it lower. So within something like a protein, the hydrogen bond energy would be pretty much, well, considerably less than 5 that you would have in the gas phase. So you really, it's apples and oranges when you're looking at energies in the gas phase or by calculations, and when you're comparing that to what you would get in solution. Okay, so next issue, for you guys who are looking for them, how do you know if you find one? Okay, so the way people typically do this is, first of all, geometric. If in a crystal structure, one sees something like that, where this angle theta is in the neighborhood of 180. Typically, that's 160 or more, sometimes 150. The second is how far apart the H is from the B. Typically, that will be less than 3 angstroms. Crystallographers, that's how they make their living. They get these geometries. And if they see these conditions are met, they'll typically check it off. Yes, that's a hydrogen bond. But there's another issue of how to, other ways of finding that. So the other means is typically under the heading of spectroscopy. So there's a couple of ways of doing that. First is NMR. And in NMR, it's pretty well accepted that in a hydrogen bond like this, the signal of this proton, so they would say proton spectrum, will be downfield. That's one word they would use for it. Or they would say delta rises. Delta is another way, larger delta is another way of saying a downfield shift. Or they would say that the shielding on the hydrogen is dropping. And typically that could be 1 to 4 parts per million. That's the units NMR spectroscopists use. So if you're looking at an NMR spectrum, if you think there's a hydrogen bond, that's the main thing that you would look for. Okay, that's not the only thing. There's also IR, or vibrational spectra. That's another key indicator of that. So in this system, all covalent bonds vibrate. In other words, it's like there's a spring between them, and they vibrate like this. And that has its result is the frequency, Greek letter nu, will usually drop when the hydrogen bond is taking place there. So for example, if it was 2,600 reciprocal centimeters or wave numbers in the isolated molecule, when it forms a hydrogen bond, it may drop to maybe 2,300. It's notable. It's clearly visible in the spectrum. And that's called a red shift. So if you find a red shift of this, whatever AH stretching frequency, that's a clear indicator that you have a hydrogen bond. And it turns out that the magnitude of the red shift is proportional to the energy of the hydrogen bond. That is frequently called the Badger-Bauer rule. And not strictly, I mean, it's not exactly, but the larger the red shift, the stronger the hydrogen bond. Complication of that is I sort of led you down a garden path again when I suggested that this is a pure vibration. Typically, this OH, for example, might be bonded to this. Let's say even something as simple as methanol. This stretch is frequently coupled with other stretches. So when you look at the IR spectrum, you don't necessarily see, you see lines, but it's hard to say this one, for example, is a pure OH stretch. It'll be typically mixed with other vibrations within the molecule. Nevertheless, the OH or NH stretching frequency tends to be fairly well defined. So that makes the use of the IR spectra fairly good, fairly useful. So NMR and IR spectra are chief tools to verify whether there's a hydrogen bond. And X-ray crystallographers tend to focus much more on the distances, the geometries. Okay. How do we in the theoretical computational business define if there's a hydrogen bond? We can calculate the NMR spectrum, we can calculate the IR spectrum, but we have additional tools that we can use. One of which, Zygmunt, has started to use in his studies of these systems, and it comes through something called atoms in molecules. I'm not going to go into the details of that, but in essence, here's an AHB hydrogen bond. You can actually measure through X-ray crystallography, but it's much more easier to do it computationally, the electron density. So the electron density you could think of as a contour surface. It has high points and low points. From the topology of this density, we can actually say whether there is in fact a hydrogen bond between there. Because what will appear in the analysis is what's called a bond path between the H and the B atom. And so there's the bond path, and there's also a point called a bond critical point, which has several aspects. It has the density itself, it has the Laplacian of the density, and there are certain energy densities as well. If there's a hydrogen bond, we can evaluate simply the density at this bond critical point. And the larger this density, the stronger the hydrogen bond. So that's a good way to do that. And where that is particularly useful, so let's say we have AH here. Here's another molecule with a B, CH, D. So here's a pair of molecules which potentially have two hydrogen bonds between them. So this will have a total strength, how much energy it takes to pull them completely apart. But the question is, how much is due to that bond and how much is due to that bond? That's where AIM comes in, because with AIM, I'll get a bond path and another bond path. They'll each have their own density. And if, let's say, let's go 1 and 2, if rho 1 is much greater than rho 2, I could say most of the hydrogen bond strength comes from this bond and less from that. I can quantify that. So if, let's say, rho 1 is 0.053 and rho 2 is 0.026, I could say with some certainty that the first hydrogen bond is roughly twice as strong as the second. That's not something which is easily determined by experimental measures. So it's quite possible that, let me say, if the two hydrogen bonds, again, here they are, they may have quite comparable distances between them. So a crystallographer would say, well, so the two distances look about the same. The hydrogen bond strengths should be about the same. But that's not taking into account the fact that this may be a much better donor than this, or this might be a better base than this. You don't see that in crystals. But when you do a quantum calculation and you apply this simple tool, the geometries become, you're much less dependent on the geometries. So computational chemistry adds another tool to all of this. Okay, now, I think if I understand what your group does, you're interested in finding out, is there a hydrogen bond? So again, here's AH, here's B. Is there a hydrogen bond there? So computationally, we can look at that computationally and say yes or no. So the question is, when does a hydrogen bond fade to black, so to speak? That is, when is there a hydrogen bond and when is there not? So typically, if you look at in terms of this distance r, the energy of the hydrogen bond tends to look like this. It fades out exponentially. So even at a long distance, it's not to say the hydrogen bond is vanished entirely, but if this is only maybe 5 or 10% the strength of a real hydrogen bond, you might not want to even think of it as a hydrogen bond. So for a computational chemist, the question, if you ask, is there a hydrogen bond there? We would say, well, give me a threshold. Let's say here. If the hydrogen bond has to be that strong or stronger to be considered a hydrogen bond, then we could say that's the threshold. If you decide you want the threshold to be a weaker one, maybe here, then that would be the threshold. So the point I'm trying to make here is that whether or not you have a hydrogen bond present, it's the question has to be better defined. How strong a hydrogen bond is a hydrogen bond? And different people in the literature will have different ways of answering because they have different questions. So as I said before, the NMR would be reflected in the change of delta. That also requires a threshold. Does it have to be greater than 1 ppm or maybe a half? That depends too. And I think Zygmunt will be talking a great deal about weak hydrogen bonds, by which he'll mean those. Those are weaker. And so this question of, is there a hydrogen bond there or not, becomes more of a question of, well, where's your threshold? Where do you decide there's a hydrogen bond there or not? Okay, so let me pause here and see if there's any questions, or does anyone want me to elaborate on anything I've talked about so far?
So thank you, Steve. Indeed, questions.
May I come back
yeah,
to
please.
this problem of double minimum?
Yes, please, double minimum. Yeah, very good.
Very often, hydrogen bonds have two possible energetic minima, two possible positions for proton between the A and B atoms. Of course, well, except the very strong and short hydrogen bonds like in hydrofluoric acid. But and again, if hydrogen bonds involve the CH bond, then obviously proton will be always closer to carbon than the acceptor. But in water, for example, in pure water, definitely the hydrogen bond between two oxygens is more or less symmetric. So the proton will have two alternative positions to take. Each water molecule may be involved in 4 hydrogen bonds. It's tetrahedral, in tetrahedral coordination.
Yes,
So-
would you like me to elaborate on that?
Sorry?
Would you like me to elaborate on that question?
No, just point out that this is possible.
Yes.
This phenomenon in water actually, I think, is responsible for very unusual physicochemical properties of water.
Yes, in fact, that has an interesting implication of proton wires. I don't know if you've heard of this concept, but in water, particularly in ice, where it's a regular order, so I'll just put 3 of them. What can happen is this proton will shift because there's a double minimum, which will cause this one to transfer, which will cause that one to transfer. And in the biological physics community, that's sometimes called a proton wire. That's why the proton conductivity of ice is quite high, because you have these pre-existing chains of hydrogen bonds, and you can get that. But if you talk about a single hydrogen bond, typically there's a double proton transfer potential. Call this AHB, AHB. And typically there's a significant energy difference between them. And typically there's an energy barrier they have to get over. And the stronger the hydrogen bond, the shorter it is. And the shorter it is, the barrier shrinks. So to elaborate on your point, there will typically be 2 minima, not always, and there will typically be an energy barrier between them. And the weaker and longer the hydrogen bond, the higher the barrier, which will make such transfers less frequent.
But the transfer may be over the barrier or sometimes through the barrier by quantum chemical tunneling.
That's right. That's right. In fact, in the case of proton transfer, tunneling is the dominant mechanism because the proton is so light, it can tunnel more easily than any other nucleus. So proton tunneling is at least substantial, if not the dominant factor in these proton transfer processes. Yes.
Thank you, Steven.
Yes, thank you. Steve, may I ask if you'd like to continue, or you have finished and we are now discussing questions?
There's just one thing I'm going to mention. I'm going to introduce somewhat related but different topic.
Okay.
So here's a hydrogen bond. And if you remember what I said about it, suppose I were to replace A by a halogen atom. It's very electronegative. So instead of this polarization, it would tend to look like that. So in most people's opinions, that would preclude an attractive interaction. But it turns out, if you look at the electron distribution, it looks like that around the X. It's negative to the sides and positive that way. This is called a sigma hole. So because the X has a positive region there, it can form a hydrogen bond to a base. This is called a halogen bond, a term which is becoming increasingly prevalent in the literature. So without going into much detail, because you guys are interested in hydrogen bonds, I just want you to be aware that hydrogen bond has a lot of cousins, one of which is called the halogen bond, and its characteristics are very similar to the hydrogen bond. And as you guys are interested in proteins, you will find mention of halogen bonds in proteins if there are halogen atoms within the protein ligand complex, whatever it's attached to. So I will leave it at that. So I just wanted to introduce that issue for any of you guys who are interested. Oh, one last thing I didn't talk about. which I think Zygmunt had mentioned might be useful. So here's AX. Suppose this is nonlinear like this. If that's the case, another base could sneak in there. In other words, both bases are using the same proton. And that is commonly called a bifurcated hydrogen bond. Is it better or worse? So each of these bonds is weaker because neither is linear. So each of these two individual hydrogen bonds is weaker than if it had been linear, but there's 2 versus 1. So it can be that a bifurcated hydrogen bond, 2 can be better than 1, even if they're both weaker, or it can be weaker than 1, and it all depends. And the last thing is the base 2. That could also have, in this case, 2 proton donors. This is also a bifurcated hydrogen bond, but here one base is sharing 2 proton donors. So I'm not going to get into a lot of detail, but this is something that will arise in protein structures, not that unusually. They will show up from time to time.
Yes. And does it require the B atom to have 2 electron pairs or just 1?
Here,
Yes. The second
yes,
pair, the lower pair.
if it had 2, as oxygen does.
Yeah, that's what I mean.
Perfect. If this is oxygen, there's 2 lone pairs, that's great. But they can share 1.
Okay.
This could be something with 1 lone pair.
Okay.
That could be shared.
Okay.
Again, 2 is better than 1.
Yes. Okay.
Steve, thank you. May I ask if you have finished?
Yes, I think I've covered what I needed to cover, and I'm quite open to answer any other questions anyone has.
Yeah, thanks a lot. Let us thank Steve for very insightful talk. Yes, so physically and virtually, yes. Thank you very much. So now I'll stop the recording.